I hope I didn't turn off the recording. Let me just make sure. Turn it on. So question number 2 was actually, we studied 3 matrices, right, in the class. So let me check. Same, I always keep forgetting that I prefer blue one. So A1 is 0, 1, 1, 0. A2 is 0 minus I, 0. A3 is 1, 0, 0 minus 1. And I define the new matrix A as N1 A1, N2 A2, and 3 A3, right? So that makes N1 minus N1, N2, N1 minus I N2, N1 plus I N2. That's your matrix A. And also, I put the condition that N1, N2, N3 are real. And also, N1 square plus N2 square plus N3 square is equal to 1. So that was the condition for this constant N1, N2, N3, the expansion of this matrix. So the first question was whether this is Hermitian or not. So Hermitian means you have to take a joint, which is transpose and complex conjugate, right? So we can take a transpose first. Then you just replace the row by column, so it becomes N1, N1 plus I N2, N1 minus I N2 minus N1. And if we take the complex conjugate, what happens? A transpose complex conjugate, which is A dagger, is actually N1, N1 minus I N2, N1 plus I N2 minus N1. Because N1 and it's N3, right? N3. So N1, N2, N3 are real. So when you take the complex conjugate, you just change the sign of I into minus I. So it's the same as A, right? So it's Hermitian. The next question is find the eigenvalue. So finding the eigenvalue, you need to find this. N3 minus lambda, N1 minus I N2, N1 plus I N2, minus N3 minus lambda is minus N3 minus lambda, N3 plus lambda, minus, which is N1 square plus N2 square, right? So that is lambda square minus N1 square plus N2 square plus N3 square is, by the condition of constraint of the problem, what is the value of N1 square plus N2 square plus N3 square? 1. So we know the eigenvalue, right? Lambda square minus 1 is equal to 0. So lambda is plus minus 1. And the final question is to find the outer product. So say lambda plus is plus 1, lambda minus is minus 1, and this is a normalized eigenvalue. And the question was, you find the outer product, right? Without actually calculating the eigenvector. So you can use these two properties. Plus, plus, minus minus is equal to I, right? And plus plus minus minus is equal to A, right? So the rest is easy. So you just add them together. So twice of I plus A, right? Or plus plus I plus A over 2. If we subtract, twice of minus minus is I minus A. Minus minus is equal to I minus A over 2. So even though you don't know about the exact form of vector, normalized eigenvector, actually finding the normalized eigenvector is going to be nightmare, very complicated. But nevertheless, you can still find out the product. So that's your answer. So how many of you got this problem right? 1, 2. How many? There must be some. So it's actually not a very difficult problem, but I just want to know whether you understand the spectral theorem. So this question is about the spectral theorem. So, I mean, even if you don't understand, you cannot calculate this. So this can be a very interesting problem, right? Actually, without calculating the eigenvectors, you can still find the outer product, which would be very useful in the future. And I was talking something about the positive matrix. So matrix A is positive. Actually, I've covered a little bit of this in the last week. So matrix A is positive if and only if for any vector or cat vector V such that V over A over V is always greater than or 0. So all the eigenvalue problems we have considered so far is not positive, except the last problem that I gave in the question. That you have 0, 1, 2, so you have positive. And if A is any matrix, which is n by n, interesting thing is you can define M as A dagger A. Then adjoint of M is A dagger A dagger is A dagger A dagger dagger is A dagger A is M. So even though A may not be Hermitian matrix, the new matrix formed by multiplying A dagger A is Hermitian matrix. Moreover, M is positive. That can be easily seen that AV adjoint. If you take the adjoint, you always change the order, right? So it becomes VA adjoint. So VA adjoint with AV is actually always positive, right? It's the same vector. Using this property, we can state the following theorem, another important theorem, and which has a very important application for many inner product with the same vector is always positive, right? So, I mean, you can regard this way. Say B is AV, then this B is free A dagger, and the inner product with itself is always positive, right? Free A dagger A free is always positive. And probably after spectral theorem, this is probably the most important properties of a matrix. That is polar decomposition. Polar decomposition is actually very important as application to deep learning. Everybody knows deep learning these days, right? And so A is any n by n matrix. Then A can be written as U root A dagger A. And U is a unitary matrix. Unitary means U dagger is U inverse. So any matrix can be actually product of this unitary with the square root of A dagger A. This property is called polar decomposition. Then A can be represented by the expansion of something similar to spectral theorem. So let's say M, A dagger A. We have found that this is a Hermitian, right? Hermitian and positive. So what happens if we have a Hermitian matrix? We can expand it using spectral theorem, right? So you must be familiar with this process, right? Spectral theorem. And of course, this lambda I is orthonormal vectors. then using spectral theorem, you can actually calculate this m, right? Square root of m. Square root of lambda I. We can calculate up to this part, right? So maybe you can save some space here. So we define a new vector, set a new vector, say psi I, multiplied by a lambda I, normalize it. And from this, define a new normalized vector, square root of lambda I over psi I. So this is 1, this is 2. And let's check the properties for EI. So EI, EJ, see what happens. Then according to the definition, square root of lambda I, lambda J, psi I, psi J, but lambda I, lambda J, which is lambda I square, A, dagger A, lambda J, tilde. Is equal to, well, A plus A dagger A can be represented by this spectral theorem, right? So we have square root of lambda I, lambda J, lambda I tilde. Let's expand by K, lambda K, and lambda J. So let's focus on this. This is K. So they are orthonormal vectors. Right. So inner product between lambda K and lambda J is 1 if K and J are the same, or 0 when K and J are different, right? So it has to be just lambda K. Oops. So since this is delta Kj, we have this square root of lambda I, lambda J, and lambda J, lambda I, lambda J. This is again delta Ij, right? So the inner product is when I and J are different, it is 0. When I and J are the same, it's lambda I divided by square root of lambda I square, which is 1. So actually this is delta Ij. So what you can see is this new vector is also an orthonormal vectors. A bit hazy, right? Am I going a little too fast? Okay. So I will give you a few minutes, maybe 1 minute to copy this I'm going to repeat. The idea is to show that for any given matrix, this matrix A can be decomposed into product of unitary matrix and Hermitian matrix. So we first find the Hermitian matrix generated from A, which is multiplied by A dagger A. And then we represent it using this spectral theorem. And then this lambda I tilde is orthonormal vectors. You are already familiar with that part, right? And then we define a new vector called phi I by multiplying A to this lambda I. And then divide by the square root of our eigenvector, and we define EI. So I'm curious whether this EI is also orthonormal vectors. So we need to check that. We take the inner product between EI and EJ, then this is just square root of lambda I, lambda j, and then phi I, phi j. But from the original definition of this, which is lambda A dagger A, lambda j, right? But this A dagger A can be represented by spectral theorem again, using this. So instead of, so we introduce something extra in this k. So lambda k, and then this outer product. And then you have an inner product with lambda I and lambda j. The first part, this is 1 when j and k are the same, or different, 0 when k and I are different, right? So then is, of all the k, only j survives. So this lambda k becomes lambda j, and this becomes lambda I, lambda j. But this is again orthogonal. When I and j are the same, it is 1. I and j are different, it is 0. So after all this delta ij. So far we discovered that this EI is also an orthonormal vector. So using this knowledge, we define a new vector. So can I move on? So define U as EI lambda I tilde. And let's check whether this is a unitary or not. So U dagger is obviously this. If we take a joint, we just need to change. So become lambda I tilde EI. Or you can use a different index, say J lambda J tilde EJ. So U dagger U is what? J I lambda J EJ EI lambda I. And we have just showed that these are orthonormal vectors. So I and j are different, it is 0. And I and j are the same, it is 1, right? So it simply becomes and we know this property, right? Which is I. So that means U dagger is U inverse. So we just show that U is unitary. And let's see what happens to this. U square root of A dagger A, say lambda I tilde. K, by definition EK, lambda K tilde. And we have L square root of lambda L and lambda I. The first thing is k L square root of lambda L E k lambda k lambda L lambda L lambda I. Firstly, k and L has to be the same, right? Otherwise it's all 0. Correct? When k and L are different, it is all 0. So one of the summation has to be just L. So it becomes lambda L EL lambda K lambda L I. But this inner product is again has to be L has to be I, right? Otherwise it's all 0. So I'll put some space here. So this actually goes to this. It becomes simply lambda I EI or according to the original definition, this is phi I A lambda I tilde. So that means this has to be same as this for all different lambda I, right? So for all lambda I tilde, we have A is U square root of A dagger A. So this is a proof of polar decomposition property. Very unique. So this polar decomposition has been used widely in deep learning problems, or AI, or quantum computation. So polar decomposition deep learning and quantum computation. So it's a very important mathematical properties that you need to know. So if you understand the polar decomposition, then at least you can start reading any deep learning books, as long as mathematics is concerned. Of course, we need to do some examples, right? Because it's all theory to abstract. Am I still going too fast? So here is actually the very usefulness of using cat and bracket notation. So you can just visualize all the process very easily using this process. So actually, let's try to do some calculations. So say A, 11 minus 5 minus 210. Let me just make sure that this is a right example. (11 minus 5 minus 10). So if I ask you whether A is Hermitian or not, is it Hermitian or not? It's not Hermitian, right? So what is A dagger? 11 minus 2 minus 5, 10, right? So obviously which is A. How about M? A dagger A. 11 minus 2 minus 5, 10. 11 minus 5 minus 2, 10. Okay, what is 11 times 11? 121. And plus 4 is 125. Minus 55 minus 20 is minus 75. Minus 55 minus 20 is again minus 75. And finally, 125. So is this matrix Hermitian or not? Hermitian, right? So let's calculate the eigenvalue for step 1. Oh, looks quite difficult problem. So 125 minus lambda square minus 75 square. Oh, I think I can do that. 125 minus lambda. Minus 75. 125 minus lambda plus 75, right? So that is 50 minus lambda, 200 minus lambda. So lambda 1 is 50, lambda 2 is 200. Step 2. We need to find the normalized eigenvector, right? From M. Are you following me, or I'm going too fast there? So what happens? Oops. Accidentally. Okay. Eigenvectors. M is 125 minus 75 minus 75, 125. So let's lambda 1 was 50. We don't know x, y, right? So M lambda 1 is 125 minus 75 minus 75, 125. X, y is 50 x, y. So this part is 105x minus 75y minus 75x plus 105y is 50x, 50y. So 75x minus 75y is equal to 0, right? Or minus 75x plus 75y is equal to 0. So that means x equal to y, right? So lambda 1 is 1, 1, and we can normalize it. So normalized eigenvector will be square root of 2, 1, 1, right? That's your first vector. Second eigenvalue was 200, so finding normalized eigenvectors. So M is, just remember that 125 minus 75 minus 75, 125, right? Let me. We don't need this anymore, so let's delete this. Lambda 2 was 200, and so M lambda 2, you can again xy. Am I going a little too fast? Okay, so M lambda 2 is 125 minus 75 minus 75, 125 xy, which is 125x minus 75y minus 75x plus 125y is 200xy. So minus 75x minus 75y is equal to 0. That means y is minus x. So we can try to set lambda 2 as 1 minus 1. Then we can easily normalize. So lambda 2 normalized eigenvector, square root of 2, 1 minus 1. Can I move on? So starting with A, 11 minus 5 minus 2, 10. We have M, 125 minus 75 minus 75, 125. We have two eigenvalues, 150. Normalized eigenvectors are square root of 2, 1, 1. Lambda 2 is 200. Lambda 2 is square root of 2, 1 minus 1. So next step is defining the unitary matrix, but we just follow psi 1, A lambda 1 tilde, right? Which is 11 minus 5 minus 5, 10. We have square root of 2, 1, 1, which is square root of 2. 11 minus 5 is 6. Minus 2 plus 10 is 8. And E1 is defined as square root of lambda 1 psi 1, right? So, which is square root of 2, square root of 50, 6 over 8. So that is square root of 50 is 25 times 2. So 5 times square root of 2, square root of 2, 6 over 8, which is 10, 5 over 3, 4. And we can check it, this is 1. 1 over 25, 3, 4, 3, 4. This is a famous Pythagoras theorem, right? 9 plus 16 is equal to 1. How about phi 2 is a lambda 2 square root of 2, 11 minus 5 minus 5, 10, 1 minus 1, square root of 2, 11 plus 5 is 16, minus 2, minus 10 is minus 22, right? So we have some space here. So that is 1. One, 2. E2 square root of 200 over phi 2 is 10 times square root of 2, right? Times square root of 2. 16 minus 22 is actually 1 over 10. 8 minus 11. Let me just make sure everything is correct. 11 minus 5 minus 5. 16 minus 2 minus 22, right? Correct? Minus 2 minus 12. 12. So 6, 5, 4 minus 3. Correct? Yeah, I could make a big mistake. So let's check whether this E2 is 1. This is 3. E2 is 1 over 25. 25 is equal to 1, right? They are normalized. So we have lambda 1, lambda 2, E1, E2, very complicated. And we also need to check that this E1, E2 are orthogonal. So E1 was, where was it? 5. 1 over 5, 3, 4. E2 was 4 minus 3. So 4 minus 3. E1 was 1 over 5, 3, 4, right? E2 was 1 over 5, 4 minus 3. Let me just double check. So E1, E2 is 25, 3, 4, 4 minus 3, 0. So E1, E2, orthogonal. So we define a new matrix, E1, lambda 1 tilde, E2, lambda 2 tilde. So E1 was 1 over 5, 4 minus 3, square root of 2, 1, 1, right? E2 was 1 over 5. Oh, sorry, I think I made some mistake. 3, 4, right? 3, 4, 1, 1. That's 4 minus 3, 1, 1. Or minus 1, right? And we have a square root of 2. So that is 5 square root of 2, 3, 3, 4, 4, plus 5 square root of 2, 4 minus 4, minus 3, 3. So that is 5 square root of 2, 7, 7, minus 1, 1, right? Let me double check. 5, 5, square root of 3, 3, 4, 4, 4 minus 4, minus 7, 1. So U is 7. So U 5 square root of 2, 7 minus 1, 1, 7, right? Next step is whether it's unitary. So U dagger is 1 over 5 square root of 2, 7, 1 minus 1, 7. So U dagger U is 25 times 20, 50. 7 minus 1, 1, 7. 7, 1 minus 1, 7. Uh-oh. This is 49 plus 1? 50, right? Second. 7 minus 7? 0. 0. 7 minus 7? 0. Finally, 1 plus 49, 50. Identity, right? So U is unitary. And finally, you need to calculate M plus. So M was and square root of M, 50, square root of 50, lambda 1 tilde, lambda 1 tilde, right? Plus square root of 200, lambda 2 tilde, lambda 2 tilde. So we need to have information about the U, and so maybe next page. Time to make a copy. So square root of M seven minus minus, right? So U 7 minus 1 this 1. Minus 1, 1, 7, right? So was 7 minus 1, 1, 7. Using square root of M is actually A dagger A. 1 over square root of 50, lambda 1 tilde, lambda 1 tilde, plus square root of 200, lambda 2 tilde, lambda 2 tilde. So that is 5 square root of 2. And this gives 1/2, 1, 1, 1, 1, right? That is 10 times square root of 2. And we have additional 1, 2. 1 minus 1, 1 minus 1. So that is 10 square root of 2, 1, 1, 1, 1, plus 20 square root of 2, 1 minus 1, minus 1, 1. So how do we do that? 10, 10, 20. So make it 20, 22, 2, 2, 2, 2, plus 20 square root of 2, 1 minus 1 minus 1, 1. So 20 square root of 2, 3, 1, 1, 3. So let me double check before I move to the next page. So square root of n is actually square root of a over a, and I think I made some mistake. I shouldn't divide by this is here, right? So all the coefficient was wrong. So that is 2 square root of 2, right? There's 10 square root of 2. So square root of 2. 5. Two over 5, and this 5 square root of 2. Correct? I must be very sloppy. I don't know why. No. So let me just double check. So square root of n is a, they go a square root. So this square root of eigenvalue, 50, 200, lambda 1, lambda 1, lambda 2, lambda 2. So this 50 is 25 times 2 is 5 square root of 2, and then you have 1 divided by 2, right? 1, 1, 1, 1. 200 is 100 times 2, which is 10 square root of 2, divided by 2 is 1, 1, 1 minus 1. So that's actually 5. So we can actually combine them with 2 over 5 square root of 2, 1, 1, 1, 1. 2 over 5 square root of 2, 2 minus 2, minus 2, 1. Actually, the answer has been quite different. So 2, 5 square root of 2, 3 minus 1, minus 1, 3. Just square root of 1. What was the u? U was 7, 7 minus 1, 1. Let me just double check. We can multiply here. Let's do that here. Because I hate going that way. So that's 1, 2. So u square root of m (7 minus 1, 1, 7) times 5 square root over 2, 3 minus 1, minus 1, 3 is 1/2. 7 minus 1, 1, 7. 3 minus 1, minus 1, 3 is 1/2. So the first thing is 21 plus 1, right? So 22. Second, minus 7 minus 10 minus 3 is minus 10, right? So this gives minus 7 minus 3 is minus 10. And 3 minus 7 is minus 4. So this minus 4. And 1 plus minus 1 something is wrong. Plus 1. Minus 1. So 1 minus 1 minus 7. It is minus 20, but I think something is wrong. 3 minus 1 1. This is 1 1 1 1. 3 minus, right? So this is actually, it has to be 3. Let's see where I made a mistake. Oh, it's 2. It's 2. Still, 3 minus 3 minus 3. And u was, let me check. U, so 7 minus 1, 7, so 3, 20. Minus 22. Where is this? Minus 1. Oh, sorry. Oh, yeah. 20. So actually I didn't make a mistake. So it's 11 minus 5 minus 2, 10. Which is same as 8. Wow. I was a bit nervous because I made a mistake. So now you can believe that there is a polar decomposition process that expand any square matrix into as a product of a unitary with Hermitian. And with Hermitian, you can always, so that's the beauty. So can I move on? So since A is, for any A, now we know that A can be written as U square root of A dagger A, and U so something pseudo similar. And also, previously, we also found that any Hermitian matrix can be also this is Hermitian, right? Positive Hermitian. So it can be represented as some unitary D T dagger. So T is actually made with lambda 1 tilde, lambda n tilde. D is a diagonal matrix, root lambda 1, root lambda n. Then, using this notation, then A can be written as U T D T plus. So we can say this is Q R. They are both unitary. Then A can be written A can be also written as A is QDR. Q R unitary. D is diagonal. This expansion has a name for the singular value decomposition. It's called singular value decomposition. But basically, the singular value decomposition is the same as polar decomposition. So you only need to understand how to do the polar decomposition. Then the rest is nature. But singular value decomposition is also widely used in deep learning. So this is about the topic that I'm going to cover for the linear algebra part. And the next topic will be differential equations. So any questions about the topics that covered today? Polar decomposition. So polar decomposition can be a good problem for next quiz, right? So maybe I'll give you some homework, like try 5. So 2 by 2 was easy, so maybe you can try 3, arbitrary matrix. So homework. A polar decomposition. That is homework. So you have learned how to do that for 2 by 2 today, right? So maybe next quiz I can ask for 2 by 2 and 3 by 3. Even 2 by 2 actually take quite a long time, almost 40 minutes. So maybe you can do some practice with the 3 by 3 polar decomposition. Maybe you can try 5 problems. Will be good enough for you for the weekend? So any questions? If not, just go briefly for next topic. Or maybe stop today? Okay. So let's continue our discussion. Let's start to actually begin a new discussion about differential equation next week. So don't forget to do the homework at home. The polar decomposition is very important. So it's actually one step beyond spectral decomposition, so you can enlarge your horizon into the general matrices.